So I've been threatening, cajoling for weeks now that we're going to start thermodynamics, and nothing to be frightened of. What does thermo mean? So if I said thermo to you, what is that? What word does that pop into your head?
Temperature?
Yeah, it means, well, temperature actually means heat. But yeah, temperature or heat. We know it's not the same thing. We use one to measure the other, but we'll get to that. And when I say dynamics, what does that mean? If something's dynamic, if we say someone is dynamic, what does that mean?
Activity or motion?
Yeah, it means it's active, it's moving. And so all we're going to be talking about is just the movement of heat or energy from one place to another place. That's it. That's really all thermodynamics means. Moving energy from one place to another. So what's that picture I've got on the screen? What is that? You probably recognize what that might be.
An explosion.
What kind of explosion? The shape of the cloud sort of gives it away. It's a very specific kind of explosion.
Volcanic.
Mm-mm.
Nuclear.
There you go. Yeah, it's actually an atom bomb being tested. Now, would this be an example of a chemical change? Because we're going to be studying chemical changes and the heat and energy involved with them. So would that be a chemical change? There's no harm in guessing.
Yes.
Okay, I got a yes. Anybody disagree? Nobody disagrees. That means everybody thinks it's a chemical change. It isn't. And it isn't because electrons aren't involved. This is a nuclear explosion. So all the energy is coming out of the nucleus being split. And so since electrons aren't involved, we don't actually call it a chemical reaction. We call it a nuclear reaction. So what we're going to be studying, since we've been studying this all term, and I keep coming back to it, we might as well call this class electronics because it all comes back to electrons. And that's what we're going to be looking at. Chemical reactions involving electrons moving from one place to another. And when they do that, a lot of times we see a difference in energy. We've probably run into it before. Like, who's sprained their ankle and someone handed them an ice pack? Like, probably everybody, right? When you get the ice pack, is it cold? If it hasn't been like broken, it hasn't been squished, is it cold?
No.
No, it's room temperature, right? And then you squeeze it or you smack it against something, and there's a little membrane inside that breaks, and then two chemicals from either sides of the bag come in contact, and then what happens?
It's cold.
Yeah, it gets really cold, right? What kind of reaction do we call that? So is that energy going into the bag or coming out of the bag?
Coming out.
So it's energy coming out, but it's cold though. Normally if the energy is coming out, doesn't it get hot? Someone's listening to music. So what do you think? Is it, I would say to you, and we're gonna review this again, of course. That's energy going in. It's actually taking energy out of your hands So your hands are warm. It takes energy out of your hands and moves it into the bag. And that's why it feels cold. So what sort of reaction is that? You know, there's two kinds. There's exothermic
Endothermic.
and endothermic. Which one's that?
Endothermic.
Endothermic, right, because it gets cold. And an endothermic reaction takes heat from its surroundings and it moves it into the reaction. And so we're going to talk about that and a lot of other things in this particular chapter. And we're going to learn how to measure these things. And we'll do some labs next week where you will actually measure temperature changes and then be able to convert that to actual energy changes. So we're going to talk about different forms of energy. When we think about energy, we really only think of basically two different kinds, right? We think of like potential energy and kinetic energy. So like if I have a rock at the top of a hill. So here's my hill. I've got a rock on the top of it. I say it's got potential energy because gravity is pushing down on it. And so the minute I just sort of give it a little push, then it starts moving. And then that would be kinetic energy. So while it's not moving, it has potential energy. Same thing's true in chemistry. We say that chemical bonds have potential energy in them because the formation of bonds and the breaking of bonds both involve energy. And we'll talk about what kind of energy that is. Enthalpy, we'll see, is a specific thing that chemists use. I don't think you hear that much outside of chemistry. And all that means is that energy changes that happen when the pressure doesn't change. Because of a lot of reactions, gas is released. And when gas is released, we have changes in volume, we have changes in pressure, and that involves work. That involves work being done. Gases want to push against something. They increase the pressure of wherever they're in. They're actually doing work. And enthalpy, we're actually measuring the amount of energy, like in a reaction that doesn't involve gas, like that involves two chemicals in a solution or in a liquid or solid or something like that. And we'll go over what that means a little bit more. And calorimetry is what we're actually going to be doing in the lab. Like if we were in real life, as we've mentioned before, you'd be doing this with a coffee cup, and I'd show you how to set it up. Basically, what it is you do a reaction inside a vessel that contains water. We measure the temperature of the water before and after, and the change in the temperature gives us an idea about whether heat has been released or heat has been taken into the reaction. And so we can actually measure the heat from chemical and physical changes just by measuring the temperature of the water surrounding it. And then we'll learn that you're going to be thrilled. I know you're excited. More stoichiometry. Oh boy, oh boy, oh boy. Because when we balance, when we balance chemical equations, we balance the mass, right? We balance the mass going in. So we have moles of reactants, and when chemical change takes place, now we have moles of products, and we know that the mass is conserved. That whatever mass of stuff went into the reaction gets turned into different stuff, but it weighs the same. It's the same mass. And we're going to learn the same is true with energy. Any energy that goes in on one side has to come out the other. And so we can, when we balance equations, we have to balance their energies as well. And we can just add them up, which is kind of nice. We can just sum them all together and figure out how much energy was involved in a whole series of reactions. That leads us to Hess's law. And oh boy, you guys are going to love Hess's law. What that tells us is that if we know two reactions that can, when we put them together, make a third reaction, like basically it makes, if I have one reaction that makes one of the reagents and another reaction that makes another one of the reagents, and you put them together and they make the two products from the third reaction, we can actually add those things together to figure out what the first or second reaction would be. And then finally, we'll get to standard enthalpies of reaction, where basically you can just look up any substance, and it will give you a measure of basically how much energy did it take to create that thing. Like, you know, if I had a reaction like this, if I had H2H2 plus O2 makes water, I could just look up how much energy does it take to make hydrogen? How much energy does it take to make oxygen? How much energy does it take to make water? Add all those together, and I could figure out how much heat or energy that reaction would make without ever doing the reaction. I could just look it up. And that gives us, that makes our lives a lot easier. We can figure out what sort of change, what sort of heat change is going to occur before we even do the reaction. That helps us figure out what kind of conditions we want for that reaction. If it's endothermic, we might want to heat it up. If it's exothermic, we might want to cool it down. So having that, that capacity helps us work these things out. So thermochemistry is just a branch of thermodynamics, which is the study of energy going one place to another, getting transformed from one form to another. And we just deal with it in chemistry now. So something chemical happens, electrons are transferred, or something physical happens, like ice melts or freezes or something like that. We can calculate the amount of energy going in and out of that particular reaction. Now, we're mainly going to talk about two forms of energy, because it's really the two forms that we see when we do chemical reactions. Either heat is made, either something gets hot or something gets cool. So energy's coming out and it's hot, or energy's going in and it's cool, and work is being done. And I mentioned a lot of the work that we'll be dealing with in chemistry is work involving gases. And so when gases like push against a piston or something like that, we can actually measure that. And generally it just involves either changes in pressure or changes in volume. And we can measure those just from our gas law chapter. We can measure those pretty accurately. And we can turn that into energy, or figure out how much energy was done, how much work was done. So something to understand when we talk about, because this is going to be coming up over and over and over when we do this, we talk about these reactions. We say that there's a system. What does that mean? Well, we're talking about energy either going into a system or coming out. And when we talk about the system, basically we're just talking about the reaction itself and nothing else. So if we did a reaction inside of a flask in a solution, the system would just be the solution, not the flask, not the table the flask is on, or you poking it with your finger, or anything else, just that solution. Everything else in the universe we consider the surroundings. So there's only two things that we have to remember. What the system is, that's really all we need to remember, is what the system is, because everything else in the universe we call the surroundings. So energy is going to go either from the surroundings into the system or the other way around. And that's it. Energy is going to go, energy flows in either one direction or the other direction. And since the surroundings involve the entire universe, we don't really have to think of where else it could go. Just two directions. So a change in the energy of the system. What this also means, this is the most important thing about this. If we measure the change in heat of the surroundings, we automatically know what the change in heat of the system is, because there's only two places that heat can go. So like number 3 tells us a change in the energy of the system must be equal and opposite to the surroundings. So if we can calculate one, we know the other one is equal and opposite. So if I say the surroundings energy went up by, let's say, 350 calories. Calorie is one way we measure heat. Actually, that's why when you eat something, it's measured in calories. That's food energy. Basically, that means if those chemicals in that food were burned, and that's what happens inside your body, it's burned very slowly, but it's burned. That's the amount of energy that would be released when you burned it. And so that's where the calorie actually means energy. So if the amount of energy went up in the universe by 350, how much did the energy of the system change? Quiet. So my surroundings went up by 350 calories. I measured that. I have a thermometer and all kinds of advanced scientific equipment. So if that is true, what was the change in energy of the system? Got to be equal and opposite. Equal and opposite means when you add them together, you get 0. So here's my change on this side. What's my change on the other side?
Would it be negative 350?
It would. It would indeed. It would indeed be minus 350. That is correct. And basically, all of our measurements are based on this. So I mean, we really, believe this because it's basically impossible to measure the system. It's really hard. So what we try and do is, so it'll be minus 350 calories. Yeah, so when we add them together, we get 0. So it's really hard to measure the change in energy of the system. So what we try and do is isolate it. And that's what calorimetry is when we talk about calorimetry. We try and isolate it as much as we possibly can away from the universe, so we don't have to measure the change in energy of the entire universe. Isolate it as best we can and measure the change of the heat of the surroundings. And then that reaction we figure is going to be equal and opposite to whatever it is we measured for the surroundings. So that's basically why we really have to believe that this is true. Just like I said, the system is the contents of the flask. And even then, for instance, we're doing a reaction. Let's say we're doing a reaction where we have our flask. Here's our flask. And we're doing a reaction where we have 2 ions. Let's say we've got calcium ions and we've got phosphate ions. And generally what happens when calcium ions and phosphate ions get together?
They precipitate?
Yeah, they do. Good memory. Yeah, they precipitate because there's so much charge there that they just really want to stick together, and they're kind of tired of being around water anymore. So they stick together and they crash out, and we get this precipitate of calcium phosphate. So if we wanted to measure what heat was involved in that reaction of, 3 calciums plus 2 phosphates give us this solid. So there's our reaction. We wanted to measure that heat. Basically, all we would have to do is put like as much insulation around the flask as we possibly could. Just insulate it really well. And put a thermometer in there and measure the change of the temperature of the water. Because even the water is not involved. Because there's some small, tiny amount of water whose bonds are being broken because they used to be bonded to calcium. So this water would be bonded to calcium on its negative side, and this water would be bonded to phosphate on its positive side. So some of those waters are going to change their surroundings, but the vast majority of the water in there doesn't even, it's like nothing's happening. So they're basically the surroundings. So we would just measure the temperature of the surroundings and see what the temperature either went up, and so energy was released, or the temperature went down and energy was absorbed. But yeah, not even the water itself inside the flask is part of the system, because it's not actually involved in the reaction itself. So we're really only dealing with those elements that are innately involved in the reaction. And if water's not a product or a reactant, it's part of the surroundings too. So sort of makes the point again that the change, delta E, and now delta, we're going to be using delta a lot. So we should remember that this little symbol, this little delta, means change. Basically, that's all that means. We're going to be using that over and over and over and over again. It's basically what we're going to be doing is, like, after a chemical reaction happens, we're going to be asking, what was delta E? What was the change in energy? Was energy released into the surroundings? And so delta E would be negative. Or was the change in energy, the temperature went down, the energy went from the surroundings into the system, and then delta E would be positive. So we're always looking at we can't measure absolute energies. We can only measure the difference between this state and this state. So what we're doing, so when we talk about energy here, in the A, where we start at a high energy, and then what happens when we drop to the final state, energy then gets released. This would be an exothermic reaction. So in an exothermic reaction, we have the system is up here, and then it releases energy as heat, and now it's down here. So it's lost energy. And so we say it's negative because energy has been lost. We always basically measure energy by what happened to the system. Did the energy go up or did the energy go down? Almost always the energy goes down because when a reaction happens, usually energy is lost. Not always, as obviously with the cool bag, the ice pack will demonstrate. That's not always the case. But in most cases, energy is lost when a chemical reaction takes place. And so we say the final energy of the system is less than the initial. And that's why we give this a negative. Now, on the other hand, here's our initial state, same energy on this side, but this time we add energy from the surroundings. And this would be the case of the ice pack. So when it started, it was room temperature, but it removed energy from the surroundings, from your leg or your arm or wherever you put it, where you hurt yourself, on your shoulder. It took energy out of that and put it into the system, which sounds weird, right? Because it got cold. So you're saying it got cold and yet it absorbed energy? Yeah, because the only reason why you would feel it was cold was because if it sucked the energy, basically the thermal energy out of you, that's how it increases in energy. And the same is true opposite way. Since something gets hot, that means the energy that was in the system is now leaving it. And we can feel it as heat, like when we burn something. That energy is going from being in chemical bonds, being released as energy, and then when we feel it, and it sort of makes sense that like a big pile of ash has a lot less energy in it than a big pile of wood, right? So that's why, so we say that change in energy is negative. Any questions so far on what's positive, what's negative, what's the surroundings, what's the system? Because we need to know this pretty well. Everyone's got it. So proud of you guys. All right. So, like I said, two ways energy can be transferred. Now, this is one we're probably familiar with. We have, let's say we have a cup of tea. We got a cup of tea sitting out on our desk. We're like reading, we're doing some work. It's like super hot. It's too hot to touch. So I'm just going to let it sit for a minute. Now, after a while, the temperature comes down, right? So the temperature inside decreases. So at first, the temperature of the system was greater than the temperature of the surroundings. But if you leave it long enough, it'll come to room temperature. And then the temperature of your tea will equal the temperature of the room. And so when that happens, heat has been lost, obviously, from your hot tea and has been turned into room temperature. So the energy has gone down. And so heat's been released, and heat we refer to as Q. Why we call it Q, I have no idea. Because we call work W, that makes sense, but we call heat Q. I think it's probably because there's way too many things for H already. So like lots and lots of things in chemistry are H. And so we couldn't use it. And not everybody writes chemistry in English either. So we got to remember that. So heat transferred is measured in units called Q, and work is just work. Both are measured in the same units, and I'll get to that in a second. So if heat is released to the surroundings, Q is less than 0. So we say Q has been lost. Heat has been lost by the system. It's got to be less than 0. Now, on the other hand, same situation. Say you don't want tea. Say you're like, I got my glass of ice water right here. Now, as it's sitting there, it's absorbing heat from the surroundings, right? I mean, it feels cold to my hands, but in 10 minutes, it's going to be slightly less cold. And in 30 minutes, it's slightly less. And then eventually, it's going to be at room temperature. So it's absorbing heat from the surroundings. The temperature initially is less than room temperature, and eventually it will go to room temperature. So we say that Q is greater than 0. That Q is positive. Like the amount of heat in this system increased, and that makes sense because it was cold before and now it's warmer. Obviously, there's more heat in there. But is heat the same thing as temperature? I've asked you this before. Do you remember what the answer is?
No.
No.
No, it isn't. Heat, we don't measure. Temperature is measured in Kelvin or degrees Celsius. Heat is not. Q is not measured in degrees. So what's the difference? You remember what the difference was between heat and temperature? Or when we measure temperature, do you remember what it was we were actually measuring? Because it's related to energy, but it's not quite the same. What do you think? It was weeks ago we talked about what we measure. We measure temperature. It has something to do with energy, but it's not quite the same thing. Nothing. All right, basically, it's the measure of the average kinetic energy of molecules. So it's not the same as heat. Basically, it's measuring how fast molecules are moving in something. The faster they move, the higher the temperature. The slower they move, the lower the temperature. So when you measure the temperature of something, that's actually what you're measuring. You're measuring how quick the molecules are moving. And so when we measure energy, basically we're measuring all that stuff. We're sort of taking not the average energy, but all of it together. And anyone know what we measure energy in? You may have seen this before. So if we measure temperature in degrees, if temperature is measured in degrees or K, what do we measure energy in?
Joules.
That's right. That's right, we measure it in joules. That's the standard metric way of measuring energy. There's also calories, and I'll talk about that in a little bit because that's going to come up. But yeah, joules, excellent. So that's heat. When we're moving heat from one place to another, generally all we need to do is just measure the temperature. We measure the temperature of something, and then we figure out how much heat it takes to increase the temperature of that something. And we'll get into what that actually means. But that's what the temperature is. It measures how much thermal energy, but we don't know how much energy it takes to actually increase the temperature because it's not the same. It depends on what the system is. Water takes more energy to increase its temperature. Metals take less energy to increase their temperature. So we need both bits of information. Now, in this instance, now we're measuring work being done. Now, like I said, most of the time, not all the time, but most of the time, work in chemical reactions is being done by gas. And so we can see here on the left, this is actually the way you would have made hydrogen gas in the lab for our determination of the gas constant experiment. You just take hydrochloric acid and you dump some zinc in there, and one of the products is zinc chloride, but the other product is hydrogen gas. And so you can imagine when you create gas where there was no gas before, the pressure goes up, right? Because you're creating more gas. And so as we go to the bottom, we can see that this piston here is being pushed on by just the atmospheric pressure in the room. So we can just measure whatever the atmospheric pressure in the room was, usually around 1 atmosphere, right? That's how much is pushing in from the outside. Now we see that piston on the bottom gets pushed out. So there is a higher pressure than atmospheric inside the system. And as it's pushing the piston out, that is work, because it's actually physically moving something. That is work. So we can measure the change in pressure and volume. We'll get to this in a minute. We basically call that P delta V work, because the pressure generally stays the same, and you're just changing the volume. Like in a car with an internal combustion engine, you have a piston pushing down in the cylinder, and then when you burn the fuel, it creates CO2 and water, vapor, both gases, and a lot of other nasty gases we don't want. And it pushes that cylinder up. So it does work by pushing that cylinder. And then cylinder comes back, it squishes the fuel and the oxygen together, and then it explodes, pushes it back out again. That is work being done by the system. Now over on the other side, that's work actually being done on the system. Because this, down on the bottom, this piston is out. And now we're pushing it in. We're increasing the pressure outside, and we're pushing that piston in. So we're actually doing work to the system. So in this instance, W is greater than 0 because we're doing the work. We're putting work into the system. We're increasing the pressure inside that container. We did that. It didn't do that by itself. We did that. So we did work on the system. That's positive. When the system does work for us, it's losing energy and giving us that energy in the form of work. So that W is less than 0. Okay? So you see how, like, basically anytime the system loses something, it's negative. And anytime it gains something, it's positive. Because we're going to be using, you're going to be seeing negative and positive signs all the time in this chapter, because whenever energy is lost somewhere, it's gained somewhere else. And so we basically have to figure out where it went. And when we figure out where it went by using minus signs and plus signs. And also, since everything is going to sum to 0, we need to know who's negative and who's positive to see if we can add these things together. So here are the sign conventions. That sort of gave away the argument there a minute ago. So basically, we add the work and the heat together, and what that does is tells us what the energy change was. If we can add them both together, then we're going to know what the change in heat, what the change in energy of that system was. So if the system had work done on it and it absorbed energy, if both absorbed heat and had work done on it, then the change in energy is obviously positive, because two things were added to the system. Work was done on it and energy was added to it. So yes, now has more energy than it did before. And on the last one, if the system did work for us and it lost energy to us, that would be negative. And this is what happens inside a car engine. It's obviously doing work for us. I mean, it's moving the car, right? But it also gets really hot, right? So it's producing heat at a tremendous rate. That's why you have to have a radiator. Your radiator absorbs heat from the engine and dissipates it out to the surroundings. So it's doing both. It's making heat and it's producing work. So that change in energy is obviously negative. But then it gets a little trickier when both are happening, and sometimes it's a little negative and sometimes it's a little positive. One can be positive, one can be negative, and we have to figure out, well, how much is each one? Is it more work than heat? Is it more heat than work? You'd actually have to go in there and do some calculations. But generally, if we do work and add heat to a system, it's pretty obvious it's gained energy. And if it loses energy through heat and it does work for us, it's obviously negative. And it's just basically, it's the first law of thermodynamics. That's what we've been talking about. I didn't want to tell you that because it's generally frightening. But yes, it's the first law of thermodynamics that says that. Newton came up with this like 400 years ago, that he realized that any energy cannot be created nor destroyed, just like mass can't be created or destroyed. You just convert it from one form into another form. So there is energy in a liter of petrol, a liter of octane. There's energy in there. When I burn it, that energy is released, but I didn't destroy it. I just turned it into something else. I turned it into chemical energy, and I turned that into heat energy. So nothing was created or destroyed, just converted from one state to another. So anytime the energy of a system changes, the energy of the surroundings change exactly the opposite way. And that's why the change of everything in the universe is nothing. Nothing can be created, nothing can be destroyed, which is a little weird to think about. But yeah, basically we just convert from one kind of energy to another. Any questions about this? It's kind of a trippy thought, I think, but when you think about if there's actual energy in chemical bonds, then that's where the heat energy is coming from. Then it kind of makes sense. Man, everyone's just getting this. I mean, I'm just gonna have to go faster, obviously. You guys are understanding this far too easily. We'll just go right to the really complex stuff. All right, let's do that. All right, so as one of my geniuses noted, the unit of energy we use is the joule. It is the metric, the System International unit, metric unit is the joule. And that is, basically this was worked out by physicists. If it was up to chemists, we'd be still using the calorie. And the reason why is because a calorie makes a lot of sense for chemists, because we measure the amount of heat generally by measuring the temperature of water. And so the calorie was the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. And that comes in really, really handy. We could have used that calories forever. But no, physicists had to come, as they usually do, ruin everything. So what they did, basically the joule was developed as a mechanical energy. And the mechanical energy was the amount of energy it took to accelerate a kilogram to 1 meter square per second squared. You know, yeah, whatever. But because we don't usually do that, we measure, like, you know, boring chemists like to sit around and measure the temperature of water. So that's the difference. And a calorie is larger. It's a larger unit. It takes a little over 4 joules to make a calorie. And I'm afraid we're stuck with joules. Although, like I said, you still have kilocalories are still used in food. And food isn't 1 calorie. The actual calorie in a food, like if you say like a hamburger has 500 calories, but you're actually saying it has 500,000 calories, because food calorie is actually a kilocalorie. So that's a lot of energy. And you need about 2,000 calories a day. So what we're really saying is 2 million calories a day is enough to power you through your day. And then the other unit, which we're not really going to use ever, but you still see, where do you see this number? Anyone seen that number? There's probably not a lot of you out buying refrigerators or whatever, but that's what you usually see on, like if you buy a fridge, it'll say it uses 500 BTUs, or an air conditioner. If you buy an air conditioner, you can sit in your window or something. It'll come with how many British thermal units will it cool something. But then that's basically it. We don't really use that for anything else. So we're just going to be focused on the joule from now on. But this number, make a note of that number, because it will be showing up later.
Is that number exact?
4.184? No, I don't think it is. That's just an approximation to 4 significant digits. Yeah, it's not like 1 inch is exactly 2.54 centimeters. No, that one's an approximation.
Yes, ever since you said that, I always question it now.
Yeah, that's just weird. It's just one of those weird things. It's, you wouldn't have thought it's true, but it's actually true. So to give you an idea of like the different amounts of energy going from a small amount, like, 1 molecule in the air is generally not a lot of energy. The fission of just 1 uranium atom isn't that much energy, but when you take, a few trillion of them, it adds up. So here's a calorie up here. And then so by burning through a mole of glucose, now a mole of glucose would be like 180 calories. That's a lot of sugar. So that's well over 1 million joules. That's a lot of heat energy. And then we just go up and up and up and up. The thing that I find amazing is that every day this much solar energy falls in the earth. So you could imagine if we could just capture a 100th of 1% of it, we'd be laughing as far as energy goes, because that's a lot of thermal energy. Anyone remember what kind of radiation from the sun transmits that solar energy? Remember, we were talking about different wavelengths of light earlier. Do you remember what kind of light that was?
UV light?
No, UV light gives you skin cancer and a nice sunburn. UV light is more, has more energy in it, but we generally, it actually doesn't transmit heat. That's why you could basically you can sit on a UV bed and not get hot. You can sit on a UV bed for hours and you won't warm up. Your body will burn to a crisp, but you won't warm up at all. It's on the other end. So UV's on one end of the spectrum and this light is on the other end.
Infrared.
Infrared, right. Infrared, that actually transfers the heat from the sun. That's why you used to see in restaurants, you don't see it anymore because it's kind of disgusting, infrared heat lamps above food, keeping fries warm or something like that. Because that generates a lot of heat and transmits it. So one is higher energy, but the other one actually transmits heat from one place to another. And it's why animals who hunt very well at night, like owls, can actually see infrared light. So there's no hiding. They're like bunnies and rats or whatever, can't hide from them because you can see their heat signatures as they move. So let's just look at a couple of really basic questions to see if we can differentiate between work and heat, system surroundings, positive, negative. So this was the example I gave just a little while ago. We're burning gasoline in a car. Heat releases. We have gaseous products expand. That pushes the pistons out. So, and as I mentioned, the radiator helps keep the engine cool by basically removing excess heat from the engine. Without it, your engine would boil over. If the expanding gases do 451 joules of work on the pistons and the system releases 325 joules to the surroundings as heat, how do we calculate delta E? What's the total change in energy? In joules, in kilojoules. So what's kilo mean? So if I have a joule, what's the difference between a joule and a kilojoule? We use kilojoule a lot because a joule is very, very small. So what would be a kilojoule?
1,000.
1,000 of them, right. So 1,000 joules. And we use this one more often because generally the changes we see are much, much greater than just a few joules, usually thousands and thousands of them. So how would we do that? So the system and the surroundings, we figure out which is which. And so the piston is, the system itself is just the reactants and the products. It's not the piston, it's not the cylinder, it's not the head, it's not the gasket, it's not any of that stuff. It's just the reactants and products. That's the system. So the reactants would be, octane, oxygen, and the products would be the CO2, H2O, and all the other gases that are made. So heat's released by the system. So we already know what Q is. That's going to be negative. So if heat's lost to the surroundings, Q is negative. And we know that work is done by the expanding product gases to push the cylinders and the pistons outward. So W is negative too. So if we want to figure out what delta E is, Q is going to be negative and W is going to be negative as well. So our overall change in energy has to be negative. So let's see how we just basically just add those. So here's our Q. Q, you remember, was 325, and we figured out it was negative. W was the work done, and it was 451. And basically, this is something that car engineers are trying to change this ratio all the time. Because obviously, we would like more work and less heat, because the heat doesn't do anything for us. The heat is just wasted energy. You don't want your engine to actually to get really, really hot. You would rather it have that energy go into pushing the pistons. So we want this to go up by as much as possible and that to go down by as much as possible. That would solve a lot of problems. And that's the nice thing about electric cars, because the electric cars don't hardly produce any heat at all. So all of the energy that's expended by the batteries basically goes into doing work, which is another reason why they're basically better than gas cars for a lot of reasons. That's just one. They're much, much, much more efficient in their heat and in their work. So we add them together, we get minus 776. We just convert that to joules. We just put a period there because we've divided it by 1,000. And then there's our equivalent. 1 calorie is equivalent to 4.184 joules. So that many negative kilocalories. Okay, so basically we just figure out how many joules, and this is what we're going to be using pretty much from here on in is kilojoules, because you can see that, like, unless we're dealing with extremely small amounts of matter, generally we're dealing with like moles. We're dealing with quantities of moles. And that would be a lot of a change from one mole of something to another would involve a lot of energy. So we usually deal with kilojoules. So 2 different paths, exact same reaction going on. So again, we're sort of returning to the car idea. So I've got my long chain hydrocarbon, octane. I'm burning it with oxygen. And this is a nice balanced equation. And so if I just take that gallon of petrol and put it in a bin and just set it on fire, I'm going to get the same amount of energy from that as I would if I burned it in the car and drove it for like 30 miles. The difference being there'd be a lot more work done here, and there'd be actually no work done there at all, because there's no piston in there. I'm not making it do any work. It's just burning, it's just releasing heat. But they'd be exactly the same, because the chemical energy locked up in the octane and the oxygen are released, and then we form the same products. And so basically it's exactly the same for both. So if we can measure the amount of heat, we can calculate basically the amount of work that's done. And that's usually really how we do it. We just measure the heat that's lost, and then what was the potential amount of energy. And if they don't match, the rest must have been work in some way. All right. So here's just how we calculate work being done. As I mentioned, it's just changes in volume. It's really all we're measuring. And if the volume stays the same and the pressure changes, we basically get the same amount of work done. So, but it's usually the pressure stays constant and we just change the volume, because usually it's atmospheric pressure pushing down, like in your car engine, outside the car engine, there's atmospheric pressure. it's pushing down on the cylinder, and then the gases are pushing back against it, changing the volume. And so there's a calculation we can do that converts the change in pressure times volume into joules. And so we'll see what that conversion is. So 1 atmosphere liter. So basically, that system has changed a volume by 1 liter without changing the atmospheric pressure. So if it does that, we say it's done 101.3 joules of work, okay? So now we can use this particular equality to figure out how much work is being done. So here, we have another piston cylinder assembly. We constantly are using that because that's like 99 times out of 100, that's the work being done in a chemical reaction with gas. We can figure out differently if it's like done by batteries or whatever. But in this instance, it's pressure and volume work. So in this example, we have a volume of 125 mils. And then it expands to 652 mils. So that's my V1. My V2 is 652 mils. And that's really all the information we need to figure out how much work was done in moving that. If we assume that the external pressure doesn't change. So we have a pressure here of 988 torr. Anyone remember how we're going to calculate atmospheres from torr? How do we do that? Anyone remember what torr is? And it's not someone saying Thor with a lisp. Torr is, you remember what it's a measure of pressure.
Can you just convert it?
750 millimeters of HQ.
Yeah, a torr, yeah, exactly right. Yeah, a torr is exactly the same as 1 millimeter of mercury. That's what it is. We just get tired of saying millimeters of mercury because it's so long to say. But torr is really easy to say. And so we just multiply that by 1 atmosphere over 760 torr. Because remember, we need to calculate P and the change of P and the change in volume, okay? All right. So we have the external pressure, initial and final volumes, and we just figure out what delta V is. So delta V would just be the difference between 652 and 125. And we just multiply that by the external pressure after we've converted it to volumes, right? Because we need units, and this goes back to the gas law chapter we just did, where units were so important. Units were essential. Get the right ones, because if you didn't have the right unit, it would screw up your whole answer. And the same is true here too. So usually we need to change pressure back to atmospheres. We need to change temperature back to Kelvin. We need to, whatever volume we're given, we have to change back to liters. And that's true here as well. Our difference is about half a liter. A pressure change of the constant pressure is a little higher than 1 atmosphere. It's about 1.3 atmospheres. And you just multiply them together. And then we use the conversion at the bottom. This is the key conversion. 101.3 joules is equal to 1 atmosphere liter. And so, again, we have these sort of weird conversions where instead of just, grams per mole or moles per liter, things we can sort of sink our teeth into, Now we're getting these conversions where we're getting 2, 3, 4 units in the case of the gas constant. And in this instance, we have 3 units, joules on top, atmospheres and liters on the bottom. So if you're going to do this calculation, as I say with all calculations, make sure the units are in there. Because if you don't have them in there, you won't know whether you've got the, whether you're doing the calculation right, whether it should be multiplying by 103 or multiplying by 1 over 103. And this helps, if you can cancel all the units out and get the proper unit at the end, you probably did it right. What the hell is he doing? All right, a few minutes left. So we're going to get into like these are the units like we really use. Generally, the sort of reactions we do don't involve a change in the volume or in the pressure. Those are only when gases are formed. So when we're doing things like, well, like the precipitation reaction I mentioned before, if we're mixing calcium ions and phosphate ions and they form a product and they precipitate out, you know, no gases were harmed in the making of that reaction. And so we're dealing with something different. We're dealing with no work. No work was done. And those are the generally the chemical reactions that we're dealing with. And so we use a very specific word for that. And the specific word we use for that is called enthalpy. You've probably heard of entropy, right? Entropy and enthalpy go together. So entropy is basically a measure of how much the system breaks down in terms of you know, chaos, how much increase in randomness is done. Like if we take like 2 single molecules and we have a reaction that produces 15 different molecules, we would say that entropy is increased. Enthalpy is basically we add it to entropy, and that tells us how much energy was involved in that chemical change as well. And basically we add those together and see whether that reaction is going to go forward or whether that reaction is not going to go forward. So in this instance, delta E is the real energy, but since W is taken out, we use a new way of measuring it. We don't call it delta E anymore, we call it delta H. So enthalpy, you remember the H that way, is basically the change in energy and the change in PV work. But since that's not getting done, generally, if there's the pressure doesn't change and the volume doesn't change, whatever the energy change is enthalpy. So pretty much from now on, when we talk about energy, we're going to be talking about enthalpy, although really it means pretty much the same thing. The only difference is no work is being done. So we're going to be using, we can use the words interchangeably, but they don't mean exactly the same thing. Is if I say the enthalpy involved in a reaction, generally means I haven't done any work. So there's no change in energy, there's no change in pressure or in volume, okay? And that's the majority of the reactions we're going to be looking at. So change in heat in the system at a constant pressure. So reactions that don't involve gases or don't involve much gases, or reactions that do involve gases, but the number of moles of gases don't change. Like for instance, if I have 1 mole of gas A and 1 mole of gas B, and they produce 1 mole of gas C and 1 mole of gas D, well, then the pressure is going to be the same before and after. And so I can measure the enthalpy of that reaction. Or if reactions where the change, oops, let me go back. Reactions where the change in heat is super large compared to the change in work, like thousands of times greater. I can pretty much ignore it at that point. Even if the number of moles of gas change, if the vast majority of the energy involved is the change in Q, or the change in heat, then I just ignore the work and say that it's enthalpy. Okay, so we, chemists do cheat a little bit. I'd like to say we don't, but it's just not true. So you're probably familiar, you obviously are familiar with exothermic and endothermic processes. Just means, so we're measuring enthalpy again. Stop. So we're measuring heat going in, heat coming out. So when we're burning gases, so here we're burning methane, and we're burning it with oxygen, as you burn things with. And so you can see these are our two products. But notice, how many moles of gas do I have as reactants, and how many moles of products do I have as products?
Three and three.
3 and 3. So they're the same. So is my pressure going to change from before and after? If I burn a mole of methane in the presence of 2 moles of oxygen in a container, is the pressure of the container going to be the same before and after?
Yes,
Yeah, how come?
because the equivalent, you're just going from 3 to 3.
Yeah, I mean, actually, it'll go up a little bit because of the heat. So we know the temperature is going to go up. So the pressure will go up a little because of the heat. But the pressure will not go up because of the amount of gas. The amount of gas will be exactly the same. And we know that every mole of gas takes up the same volume, pretty much. And so the pressure will not have changed at all. And then down here, basically all this is melting ice. So I've got ice here on the bottom, H2O with a solid, and on the top, I've got liquid water, H2O with an L. And so that takes heat in. So heat is going in from the surroundings into the block of ice and turning it into a liquid. That is an endothermic process, okay? So we say that the enthalpy of the enthalpy of an endothermic process is less than 0 because it loses heat. But on the other side, we say that the enthalpy of an endothermic process is greater than 0 because it's gained heat. And we can measure that in terms of its temperature. So we know that the molecules in solid ice are not moving as quickly as the molecules in liquid ice. And that's what the temperature tells us. Sort of gives us a measure of the average thermal energy or kinetic energy of those molecules. Now, if we could also figure out how much energy it took or how much energy it takes to change solid ice at 0 degrees to liquid ice at 0 degrees, and we're going to get to this tomorrow or Monday, we could figure out exactly how much heat was absorbed. And in fact, we do know how much energy that is. So let's just, all right, so we'll finish up here. So enthalpy diagrams. Enthalpy diagrams are just basically this, showing like, where did you start? Did you start up high? Did you go low, or did you start low and go up high? So we need to figure out what change in energy took place. If it was a positive change, then we would have started low. Oops. We would have started low on the graph and increased. And if we lost energy during the chemical or physical change, anyway, which one of these changes is chemical, which one's physical? One of them's chemical and one of them's physical. Which is which?
Physical's the right side.
Right, because We haven't changed any molecules. We haven't moved any electrons anywhere. It's still water. And the water molecule is exactly the same when it's not moving as much or when it's moving more. Even when it's in a gas, it's still the same thing. Here we have broken bonds. We've broken these bonds and we have formed these ones. And so that is a chemical change. Anytime you break a bond, a chemical change has taken place. So you look at the reaction. We have two reactions here. Figure out whether delta H is positive or negative, and we'll draw an energy diagram. So I'll let you decide. So this first one here, what do you think? Would this be, you think delta H would be positive or negative? Notice that we have energy now as a product or a reactant, and that's actually how we can treat it. So what do you think it means if we have energy now? So the first one, is energy a product or a reactant? What side of the equation is it on?
It's a product.
It's a product, right? So when hydrogen mixes with oxygen and detonates, explodes, it reacts, makes water and energy. So would that be an exothermic reaction or an endothermic reaction?
Exothermic.
Yeah. Yeah, I mean, we're combusting something. It's probably exothermic. Yes, that's exo as hell. Has anyone seen the Hindenburg explode? I would say that was an exothermic reaction of hydrogen. So what would the sign of delta H be? So delta H here would be what?
Negative.
Negative.
Yes. Yeah, negative. We'd say that delta H for this would be negative 285.8 kilojoules per mole. Because basically, we use it as a reactant or a product, and we can balance it just like a reactant or a product. So if I have 1 mole of hydrogen and half a mole of oxygen, and I make 1 mole of water, basically what I say is that I make 285.8 kilojoules per mole for that reaction. So for every mole of hydrogen, I make per mole of hydrogen or per mole of water produced, either way, I make that much energy. Now let's look at the second one. Now the second one, which side of the equation is the reaction on? So with this one, which side has energy on it? The reactant side or the product side?
The reactant.
It's the reactant this time. So basically what that means is I have 2 reactants. I have liquid water and energy. And when I combine liquid water and energy, I get steam. And you think about it, well, that makes sense. You know, if I add heat to liquid water, yeah, I boil it. Duh. Yeah, that makes sense. So is that an exothermic reaction or an endothermic reaction?
Endothermic.
That is endo. Very good. So when it's endo, my delta H is
Positive.
yeah, it is. So in this instance, I'm looking at it takes 40.7 kilojoules of energy to change 1 mole of water from a liquid to a gas. That's what that means. So and we'll learn later how we're going to like calculate this. What it basically means is like at 100 degrees C, it takes an additional 40.7 kilojoules of energy to take that water, liquid water at 100 degrees C, and convert it into vapor at 100 degrees C. It takes more energy to get it to change phase from liquid to a gas. It's not enough just to get it to 100 degrees. You actually have to add even more energy to get it to move from a liquid to a gas, okay? And we will go over how we calculate all that stuff. And in fact, you can pretty much be guaranteed you're going to get a question like that on the exam, an evil and mean question like that on the exam. So you've already figured out which ones are exothermic and which ones are endothermic. These are what the diagrams would look like. Okay, so we know in the first reaction, we're going to lose energy. So our reactants go on the top. Because we have high energy reactants, they're going to lose energy, and we're going to have a lower energy product because we've lost energy as heat. It's exothermic. Energy's been released. When we burn something, energy gets released. So our high energy is in the reactants, whatever it is we're burning. And then the low energy products are going to be like the water, the CO2, whatever that's produced as products. Now on the second one, heat's a reactant this time. And so it means heat is going into the reaction. So it's real easy to figure out which side of the heat is going on. If it's going into the reaction, it's a reactant, it's going in. If it's a product, it's on the other side, it's coming out, it's being produced. And so that is an exothermic reaction. So on the bottom, we're putting heat in. So wherever we start is at lower energy, that's the liquid. And then we put additional energy in the form of heat, and then we turn it into a vapor, which is, and we know, vapor is a higher energy state than a liquid. Why? Because the molecules are moving a whole hell of a lot faster as a vapor than they do as a liquid. And by definition, higher energy state. Okay? So, I'm going to leave it there for today. We're going to pick it back up on Monday when we get into the nitty-gritty of calculating these energy changes. Any questions so far? Anyone still awake? Look how much exothermic work or endothermic work is being done here. Oh, I have a question for you before you go. We'll leave it at that. So that water has been sitting there for like about 90 minutes. So it was 0 degrees. The liquid water was 0 degrees when I started. And now about 90% of the ice is melted. What's the temperature of the water now? This relates to what we're going to learn on Monday. What do you think the temperature of the water is now?
Would it be exothermic?
No, it's endothermic because heat is going in to the water. So it's a endothermic reaction. But what do you think the temperature of the water is? It's been 90 minutes now. The ice is almost gone. So would the temperature of the water have gone up?
Yes.
What do you think? Everyone think the same thing?
Wouldn't it go down?
Well, if it goes down, it'll freeze.
It's
About room temperature then?
Well, it's still got ice in it, right?
Oh wait.
There's still ice in it, just not nearly as much as there was. This used to be full of ice. Now there's hardly any. So what do you think? So we had one person said it'd be warmer. That makes sense. Colder. It's not going to be colder because the heat of the room is heating it up. So you guys have done this. You have the, like, ice water. You drink it after, like, if there's still ice in it, is it the same temperature or is it warmer?
Isn't it slightly warmer because the ice is melting?
Ice is melting,
It's a
but
phase.
the liquid water is the same temperature.
Yeah.
So it's still 0. That sounds weird, right? I mean, it may be a little bit above at certain places, but if you mix it up, it'll still be 0. And we'll learn that on Monday, that basically all the heat that my hand and the room are going in is melting the ice. So it's all that energy is going into converting H2O solid to H2O liquid. But the temperature of the water won't change until all the ice is melting. And then when all the ice has been converted to liquid, then the temperature starts to change. So we'll learn, actually, that the temperature of something doesn't change during a phase change. Same is true here. This reaction right here takes place at 100 degrees. So if you have a pot of water and you're boiling it, you can never get it hotter than 100 degrees unless you put it under pressure, because the phase change is taking place. It's turning from a liquid to a gas, and that takes place at 100 degrees. So it's just going to stay at 100 degrees, no matter, you could have a pot that's like, 15 gallons big. It's going to stay at 100 degrees until all the liquid is gone. Now that you have gas, now you can heat the gas to whatever temperature you want. But until it's all converted to gas, the liquid is still 100 degrees. Yeah, it's weird, but true. We'll talk about it on Monday. All right, so think about that over the weekend. Scratch your head. Let me know if you're thinking full of crap. Test it for yourself. If you have a thermometer and some ice, test it at home. That's what I'm going to do right now. I'm telling you. Make sure I'm not lying to you. All right. I'll see you on Monday. If I have any announcements, I probably will have some announcements. Yeah, be sure to check in on Canvas, and yeah, all of the lectures and recitations and labs and everything will be posted this weekend. So get to that as soon as possible. And your marks will be coming out as soon as we can. Sorry about that. It's been super, super busy. All right. Have a good night and a good weekend. We'll see you on Monday. Stay safe, okay?
Thank you.
All right. Okay, thank you guys. Bye-bye.